Welcome to Introductory Chemistry with Dr. H. This is a video about calorimetry. I'm going to talk about specific heat and heat capacity, and then I'm going to talk about the two common forms of calorimetry, the constant volume kind and the constant pressure kind. Heat capacity is the amount of energy in joules needed to raise the temperature of some quantity of a substance by 1 degree Celsius. On the other hand, the specific heat is the amount of energy needed to raise 1 gram of a substance by 1 degree Celsius. So these different heat capacities have a relationship. So capital C is the heat capacity, and it's the amount of heat in joules needed to raise the temperature by 1 degree Celsius. So it has units of joules per degree Celsius. The specific heat capacity, on the other hand, is the amount of energy needed to raise just 1 gram. So its unit is joules per gram degrees Celsius. And we multiply that specific heat by a mass in grams in order to come up with the heat capacity for that larger system. So these two things are related. We can use either of them to understand how much heat is required to change the temperature of something. So if we want to use the specific heat capacity, lowercase s, we multiply that by the mass of the stuff that we're trying to raise the temperature of or cool the temperature down, right? And we multiply that by the change in temperature to come up with the amount of heat. If we have a heat capacity, meaning we know how much energy is required to raise the temperature of that whole system, all of the mass at once, we would just multiply the change in temperature by the heat capacity of that entire system in order to get the heat. Most of the time, when you're looking things up in tables, what you find is the specific heat capacity. So here's a really short table of heat capacities. And what you'll see, importantly, is water's down here close to the bottom. It has a very high specific heat, meaning it takes 4.184 joules per gram of water to raise it 1 degree Celsius. Notice there are lots of other things here, like metals, like aluminum. It's 0.9 joules per gram degree Celsius. Here's carbon, 0.5 or 0.7, depending on its form, joules per gram degree Celsius. So water takes a lot of energy to change its temperature, right? And that's something that we need to keep in mind throughout this course, but it's a super important fact. So look at lead, for example. Lead, it only takes 0.158 joules per gram. That's a tiny fraction of the amount of energy it requires to heat up water, the same amount per gram. So in any case, this is the heat capacity and the specific heat capacity. Let's get into talking about what calorimetry is and what it can be used for. Oh, I guess we're going to do an example first. So how much heat would be required to raise, to heat 35.9 grams of ethanol from 20 to 50 degrees? So these calculations are pretty straightforward as long as you have the data. So what we have is a mass in grams, and we have a table that has specific heats. So we know that it takes 2.46 joules per gram degree Celsius to raise the temperature. So we're just going to use this top equation here because we have specific heat and we have mass and we have a change of temperature. So 35.9 grams of ethanol. Now I'm going to drop in the specific heat capacity, 2.46 joules per gram degree Celsius. And the final temperature is 50 degrees and the initial temperature was 20 degrees. So 50 minus 20 is 30. And it looks like we only have 2 sig figs on that number. So 30 degrees Celsius is delta T. And when we do the math, what we find is it's 2,649.4 joules. We only have 2 significant digits. Very often we report large energy numbers in kilojoules rather than joules. So let's divide that number by 1,000 to get to kilojoules and correct for the significant figures. So it would be 2.6 kilojoules would be the amount of heat required to change the temperature from 20, raise the temperature by 30 degrees of 35.9 grams of ethanol. That's just an example of how to use these equations. Okay, let's talk about constant volume calorimetry. First, what the setup looks like, and then what we can measure by it. Constant volume calorimetry is also called bomb calorimetry, and it's not because the thing explodes. It's because we're doing a tiny explosion inside of a very rigid container in the middle of the calorimeter. So this is the way the setup looks. You have a little sample cup in the middle. In this case right here with the thick walls, that's the bomb, if you will, within the calorimeter. And you're going to put a sample in here. You're going to pump this thing full of oxygen. So all that's inside there is the sample and the oxygen. And then you're going to have 2 little ignition wires that go through holes in the bomb that are sealed. So everything inside there is sealed. So the volume of that inner cylinder cannot change. So that's why we call this a constant volume calorimeter. And when you pump it full of oxygen and you put some sample in there that can burn in oxygen, and then you heat up those ignition wires, what's going to happen is you're going to do complete combustion of whatever sample is there. because there's excess oxygen. It's, in fact, the only thing in there, the only gas in there is oxygen, and then the sample. So what's going to happen when you do a combustion, I think you have the sense that most of the time heat is released in a combustion. That heat is going to make its way through the walls of the bomb into a water bath that's surrounding it. So there's a water bath outside of the bomb that's surrounding it, and it absorbs all the heat, and we can measure very carefully the temperature change associated with that combustion to get a sense of how much heat flowed out of the bomb into the water. And so the system, if you will, is the stuff inside the bomb, and everything else is the surroundings. And so we need to keep that straight when we're doing calorimetry. And importantly, the water inside the calorimeter is also insulated, meaning there's very little heat flow out of or into the water bath that's inside. So really we can assume that all the energy that was transferred from the bomb ended up in the water and made the temperature of the water change. Okay, so that's the setup. And so now let's talk about sort of the equations a little bit. So delta E, remember that's the change of internal energy for a system, is affected by both the heat and the work that that system undergoes in some process. And we know that Q, that we can also express work as minus P delta V. But we know in this system, certainly the pressure is changing inside when we're doing that little explosion in there, but importantly, the volume doesn't change. So there can be no work done on this system. So that whole term goes to zero, and what we find is the change in internal energy is going to be equal to Q, and that's going to be equal to the Q of reaction, whatever reaction took place inside there. And so that Q of reaction, of course, is equal to negative Q of the calorimeter. So if we can monitor the heat that's absorbed by the water, we know that that's the amount of heat that was released by the reaction. So they have opposite signs. And so we can calculate that heat of reaction by looking at the calorimeter constant, which is just the heat capacity for that entire calorimeter, mostly the water, right, that's surrounding it, and the change in temperature. So importantly, here's a heat capacity that is not just water, but it's also the bomb, the walls of the bomb, and everything else that's inside the water, because that's the stuff that's all going to be changing temperature. We measure that calorimeter constant by doing a reaction that has a known heat of reaction. So we understand how much heat is released from the bomb for certain reactions, and we measure the temperature change of the calorimeter, and we can calibrate a calorimeter constant. So oftentimes when you're doing questions, when you're asked questions about calorimetry, they will have already measured that calorimeter constant, and it's your job to figure out the heat flow or the change in temperature you expect for the calorimeter. Okay, so really important. When we're doing constant volume calorimetry, what we're measuring directly is the change in the internal energy, that delta E, which is equal to the heat or to the heat flow out of the reaction. Okay, that's where we are. So let's do an example just to sort of see what something like this would look like, constant volume calorimetry. So you take 6.12 grams of glucose and you put them into your sample cup. And it was combusted in oxygen in a constant volume calorimeter. Here's our picture. And here's the calorimeter constant, this capital C, this heat capacity for the whole system, 13.8 kilojoules per degree Celsius. Okay, that's this number right here. That's how much energy it takes to raise the temperature of the whole bomb by 1 degree Celsius. It's 13.8 kilojoules. The temperature of the calorimeter increased from 25.7 degrees to 32.6 degrees. What's the change in internal energy for every mole of glucose that's burned? Okay, so we need to use this equation. Q reaction equals the calorimeter constant times the change in temperature. That will allow us to find the heat of reaction. So here we go. 13.8 kilojoules per degree Celsius, that's our calorimeter constant. The calorimeter ended up at 32.6 degrees and started at 25.7 degrees, so that's our delta T term right there. And what we see is we end up with 95.22 kilojoules with two significant digits on that because of the difference between 32 and 25. Only gives us two sig figs in that answer. So we've got 95.22 kilojoules. And that was for the combustion of 6.12 grams of glucose. So we need to figure out how many moles of glucose that represents. So let's calculate the moles of glucose. The molecular weight's given there, so we don't have to calculate it. So 6.12 grams of glucose, 180.156 grams of glucose per mole of glucose gives us 3.397 times 10 to the minus 2 moles of glucose. So that's how many moles of glucose were involved. So if we want to figure out what the change in internal energy for every mole of glucose burned, we have to divide, right? So 95.22 kilojoules divided by 3.397 times 10 to the minus 2 moles gives us, with two significant digits, 2,800 kilojoules per mole of glucose. That's the change in internal energy associated with burning 1 mole of glucose, about 2,800 kilojoules. So what you can see is that calorimetry gives us a tool to understand how much heat is flowing into or out of a system. It's a very sensitive device that allows us to understand that. Okay, let's talk about constant pressure calorimetry. Constant pressure calorimetry is much simpler to carry out. And in fact, you can do a really decent constant pressure calorimetry experiment with just a couple of styrofoam cups and a thermometer and some water. So this is a kind of calorimetry that you may have already done in a lab class somewhere. So here's the setup. They suggest putting a couple of styrofoam cups to make sure that the system is well insulated. You fill it with a known volume or mass of water, right? You cover the cup, the entire system, with a thick piece of foam that has a hole in it for a thermometer, and maybe if you want to get fancy, you can put a stir in there. Otherwise, you can just swirl it with your hand. And what you're going to do is you're going to either put something in there that's hot, and we can figure out what its heat capacity is, or we can set up some chemical reaction within that water. And really importantly, there are a few assumptions that we make when we do constant pressure calorimetry. One is that we assume that the cups don't absorb heat and that they're perfectly insulating. That's an assumption, but it works pretty well. Cups are pretty good at insulating. So if the cups are perfectly insulating, what that means is the water itself in the cup is the surroundings. And the system that we're worried about is whatever we drop into the water, usually a reaction or a hot piece of metal or something. And so the reaction itself is the system, and the water in the calorimeter is the surroundings. And we assume that that surroundings is completely isolated from the rest of the universe, right, by the styrofoam that's surrounding them. Okay, so we assume that there's negligible heat loss through the cups. Okay, so we know that the definition of enthalpy is Q at constant P, and we know that's related to the internal energy change delta E minus P delta V. So here we're working at constant pressure, and there is going to be some work done, some delta V, but we don't really care about the difference between the internal energy and the minus P delta V term, because we've defined the enthalpy change as the heat flow at constant pressure. So that's one of the reasons why it's very convenient to define enthalpy in this way, because we don't have to worry about these more detailed measurements that would be, you would need a constant volume calorimeter to sort of get at this delta E term, and we already talked about that. So let's talk more about how we do this calculation. We know that Q of the system plus Q of the surroundings equals 0 by the first law of thermodynamics, conservation of energy. And again, we're assuming that the styrofoam cups and the foam lid keeps this isolated from the rest of the universe. So Q system plus Q surroundings must be 0. Any heat lost by the system must be gained by the surroundings. And you can solve that equation for either Q system or Q surroundings, and you see that the reaction or the heat flow into or out of the reaction system is going to be equal to minus the heat that's absorbed or given up by the surroundings. And our surroundings are almost always water, and importantly, we know to a high degree of accuracy the specific heat of water, 4.184 joules per gram degree Celsius. That's the amount of energy needed to raise 1 gram of water by a degree Celsius. We also know that we often measure water in volume, but conveniently, 1 milliliter of water is equal to 1 gram of water. So regardless of whether we measure volume or whether we measure the mass of the water, either way, we can get to the mass of the water. And that's important because we're going to use this equation right here for calculating heat. And so on the water side, we're going to be able to measure the temperature of the water before and after the process takes place. We know to a high degree of accuracy the specific heat of the water, and we also know the mass of the water. So we've got a good handle on this minus Q surroundings term, right? And everything inside the cup other than the water is called the system, okay? And so the reaction or whatever process is happening in the reaction. All right, let's do a couple of examples. So here we go. I've included some of the equations we just talked about at the top here. So a sample of quartz, which has a specific heat capacity of 0.730 joules per gram degree Celsius, put into a constant pressure calorimeter that contains 150 milliliters of water. The quartz sample starts at 94.4 degrees Celsius, and the temperature of the water starts at 17 degrees Celsius. So when you put the quartz in there, the quartz is hot, evidently, right? It's 94.4 degrees. It's going to start warming up the water, and itself is going to cool down. And when the temperature stops changing of both the water and the quartz, they both end up at 21.8 degrees Celsius. So the question is, what's the mass of the quartz? And we can look right up here at the equation to figure out where we're going to relate all this information to mass. Somehow we're going to need to talk about this Q equals ms delta T, and specifically we need to relate that to the quartz, and we're given a specific heat capacity for the quartz. But let's start with the surroundings. We know the most about the surroundings. Ms, mass times specific heat times the change of temperature of the water. We have 150 grams of water because every milliliter of water is 1 gram. We know the specific heat of water is 4.184 grams per, or joules per gram degree Celsius. And we also know the temperature change. The final temperature was 21.8 and the initial temperature was 17. So that's the delta T term. And I just want to point out that when you take 21.8 minus 17.0, you end up with 4.8 degrees Celsius, and the last sig fig is that 8. So that means that difference right there has limited our significant figures in the next step to 2. So when we do this calculation, we get 3.012 times 10 to the third joules, and that 0 is the last significant digit. We're stuck with 2 sig figs because of that difference calculation. All right, so this is the Q surroundings. And we know that the Q of the system is going to be equal to negative Q of the surroundings. So I'm just going to go ahead and take that number, put a negative sign in front of it, and now I've got the Q of the system. We've already measured it. The thing is, what we don't know is the mass of the system. We don't know how much quartz we put in there, but we do know its specific heat, and we know its change in temperature. It started at 94.4 degrees and ended up at the same 21.8 degrees, so that's the change in temperature, so we just need to solve for M here. And when I did that math, assuming I didn't make any mistakes on my calculator, I got 56.8 grams when I solved for mass. I know I only have 2 sig figs here, so that's 57 point, or grams, so a number with 2 significant figures. So that's how much quartz is in this sample. That's one way you can use constant pressure calorimetry. Okay, so I mean, it's kind of a silly way because you could of course just measure the mass of that sample if you had a balance, but it's another way to access mass, but it demonstrates all of these principles nicely. So what happens more commonly in a constant pressure calorimeter is we're actually doing some chemical reaction, and what we're asking is how much energy changes when we do that reaction. This is by far the most common way we use it. And again, constant pressure calorimetry gives us direct access to the enthalpy change of some process, so in this case a reaction. So our reaction is this. We're going to take 11 grams of solid sodium hydroxide and we're going to dissolve them in 200 milliliters of water in a constant pressure calorimeter. Again, we've got to make sure that we're keeping the system and the surroundings clear. The system here is the sodium hydroxide itself. The surroundings is the water in the calorimeter, and that's it. So what's observed is the temperature change of the water from 22 degrees to 37.1 degrees over 8 minutes. None of these equations involve time, so the 8 minutes is kind of irrelevant, but you always have to figure out what information in a question is relevant. So here's the process that's happening. This is the thing that's making there be an energy change. Solid sodium hydroxide is put in water, and we know that it's a strong base and a strong electrolyte, so it's going to dissolve completely into ions. Sodium ions, aqueous, means all the sodiums are surrounded by waters. Hopefully you have a picture in your mind of what that is. All of the hydroxide ions are also surrounded by water, so that's also aqueous. That process has an energy change associated with it, evidently, because the temperature of the water changes. So let's answer a few questions about what happened here. So we observe a temperature change from 22 degrees Celsius to 37.1 degrees Celsius. So that's the water changing temperature. And the water is increasing in temperature, meaning it absorbed energy from the system. So the system is putting energy out. When a system puts energy out, we call it exothermic. So this is an exothermic process. Okay? If the water got cold, it would mean that that heat was flowing from the water into the system, and that would be endothermic. That's not what we observe. So then it says how much heat was released or absorbed by the reaction. Okay, we have the most information about the surroundings because we know the specific heat. We know the heat capacity of water, the specific heat of water. We know the mass of the water, and we know the change in temperature of the water. So let's go ahead and set that up. So we're going to solve for the heat, and this is of the surroundings. And so the mass, we're going to just do 200 grams, and it's 200 with the significant digit there, 200 grams times the specific heat of water, 4.184 joules per gram degrees Celsius, right? And I'm kind of running out of space here, and my temperature change is final temperature, 37.1 minus 22.0 degrees Celsius. So let's go ahead and just do that math. 37.1 minus 22.0 is, it's important to kind of write that difference down so you know how many sig figs you have going forward. That's 15.1. It looks like I still have 3 significant figures in that number. I'm going to multiply that by 4.184 times 200. And the heat that I get for Q surroundings, and I'm going to erase this now because it's been used, is 1.2635 times 10 to the 4th joules. And remember, we've got 3 sig figs in that number. We could convert that to kilojoules if we wanted by dividing by 1,000. So this is 1.2, or no, I'll just write it like this. 12.6 kilojoules. And so the Q of surroundings is 12.6 kilojoules. That means the Q of the system, which is what we're interested in, the Q of the system, which is the reaction, because this question is about the reaction, is negative 12.6 kilojoules. So how much heat was released or absorbed by the reaction? Well, the reaction released 12.6 kilojoules, and because it's releasing 12.6 kilojoules, we give that a negative sign. Okay, what is the delta H of reaction per mole of sodium hydroxide? Well, I guess first we need to figure out how many moles of sodium hydroxide we have, and then divide the energy change that we observe for that amount of moles. So let's see. So we have 11 grams of sodium hydroxide, and the molecular weight of sodium hydroxide is given there at the top, divided by 39.9997. And I got a number of moles of sodium hydroxide as 0.2750. So that's the number of moles of sodium hydroxide. So if we want to figure out how many kilojoules per mole, it would be minus 12.6 divided by that number. So what I get is I get a delta H of reaction of negative 45.8 kilojoules per mole. So very often that's the way we report these numbers in kilojoules per mole. So minus 45.8. The negative sign makes sense because this is an exothermic reaction, so we expect the delta H is negative. Heat is being released by the reaction into the water. Temperature of the water increases. So this is a video about calorimetry. I hope you found it useful.